Hello everyone and welcome to a video about Grignard reagent. So Grignard reagent is kind of a very versatile method to produce a CC bond or to lengthen your carbon chain. It's really good. And let's look at the structure of the Grignard reagent. Here's the structure, and the Grignard reagent has magnesium in it. Magnesium connected to some alkyl group and a halide. X here means a halide. This is a halide. So it can either be chlorine or bromine or whatever. But most commonly you would see a bromine. Sometimes iodine. That's also a possibility. And Mg is just your magnesium, right? Now, if you look at the electronegativity table, you will find that carbon has a higher electronegativity than magnesium. So you would expect the dipole arrow or the dipole arrow pointing towards the carbon. So carbon would be more nucleophilic because carbon has a higher electron density. It's kind of like a negatively charged carbon, but not quite. So this carbon is very electronegative, so it has quite a big partial negative charge, and on the magnesium, of course, it will have a partial positive charge from the dipole, right? Now let's look at how you can make Grignard reagents. Now there's one thing that you need to remember about Grignard reagents is that you need to make the reagent in anhydrous conditions. So you would use a solvent which does not have any acidic protons. So a warning for Grignard reagents is always do it in, it sounds so weird, anhydrous conditions. Or always Grignard. That sounds so weird. Alright, so to make Grignard reagents, you will need an alkyl halide, an alkyl chloride, bromide, iodide, whatever. And then you would need to treat that with magnesium in ether or in any aprotic solvents. Most commonly is ether. And you will get your Grignard reagent. So it's going to be R, Mg, Br. So, well, in this case I use X, so RMGX. And all these examples I use RMGBR. And how does it work? How does Grignard reagent works? So how it works is, as I said, the carbon on the Grignard reagent. So let's say for this one, ETMGBR. So ETMGBR looks like this. And as I said, the carbon here is quite nucleophilic. So it will find an electrophilic carbon to attack, which in this case is this carbonyl carbon, right? So what's going to happen is that the Grignard reagent will attack the carbonyl carbon, pushing the carbonyl electrons up, CO double bond up, to form a intermediate like so, OMGBR. So actually O is in a negative charge right here because we gave the electrons back to oxygen. But you know, sometimes we write it as O and then bonded to magnesium and bromine. But for me personally, when I write it out, I usually write it like this. This is how I would do it personally. But you know, this is a more accurate way of depicting this. And then you will have your ethyl group that we just added. So let's abbreviate it as ET. Good. Now, then after workup, so acidic workup, it's just an addition of acid. So this is what we call an acidic workup. You would just get your proton back on your oxygen to give you the final product, which looks like so. Okay, quite easy. It's just an addition to the carbonyl. Nothing special. In the same manner, for the ketone down here, your product should also be an alcohol, a tertiary one, with your nucleophilic group, in this case is your phenyl group, coming out. So here it is. This is your product. This is your final product. I should also label the colors. Oops, sorry. Label the colors. Let me do that real quick. ET. There you go. And then for this one, Grignard reagents, of course, if it can attack carbonyls of ketones, it can also attack carbonyls on aldehydes. So it's gonna be like this, right? And then this is the allyl group. So 1, 2, 3, like so. This will be your final product. For esters, there's gonna be something really peculiar about it. So what's going to happen is that your usual Grignard reagent chemistry happens is that your methyl Grignard, in this case, I'm gonna use the colors withdrawal mechanism, it's gonna take too long. So your methyl Grignard will attack the ester to give you this tetrahedral intermediate. O is with MGBR, an accurate depiction, and then the methyl group stems out of it. What's gonna happen next is that let me show the bonds. The OMG bond will come back and kick out the leaving group. In this case is the OR group, or the alkoxide group, to give you the ketone, right? Okay, normal, that's good. The thing is, your product, your ketone product, it's way more reactive than your ester starting material. So what's going to happen is that another molecule of Grignard will come by and attack your newly formed carbonyl, your newly formed ketone, and then you will get your tertiary alcohol, like in the first step. So when you use Grignards with esters, be careful. You will get double Grignard reactions. You will get Grignard 2 times. So Me, Me, and OH, like so. So you will get 2 additions of Grignards right here. This is the first addition, this is the second addition. So be careful every time you do Grignards with esters. But there's a way to circumvent this, is that you can use a more reactive starting material, or you can have a more stable intermediate. But we'll talk about that later. It's coming up soon. And actually, it's coming up right now. So this is a special kind of amide, which is called the Weinreb. I don't know how to pronounce it, but this is the Weinreb amide. So it's just a fancy name. It's nothing that much of a specialty, but it's just named after a person. So what's going to happen here is that your Grignard will, the same thing, will attack your Weinreb amide. So in this case, we have methyl Grignard. Okay, so attack. Now you will form your tetrahedral intermediate. NOME. MGBR. Methyl group. Good. Now, the thing is that this intermediate, this is a tetrahedral intermediate, by the way, hasn't really got any good leaving groups. This is a horrendous leaving group, of course. This can leave, but it prefers to stay. because if it leaves, you have a negative charge on the nitrogen. That's not really something that nitrogen really likes. So this intermediate will stay for some time until you do an acidic workup. So once you do the acidic workup does two things. It protonates your amide, and it also protonates your alcohol. So your oxygen. So it protonates your aldehyde. So now it becomes there should be a better way of depicting this. Maybe like that. So now your amide, it used to be an amide. So now your amide is now positively charged. And now this is kind of a better leaving group than before, right? Because now when it leaves, it doesn't have a negative charge on the nitrogen anymore. So it's more willing to leave. And the second thing that the acidic workup does is it destroys the leftover Grignards. So when you do an acidic workup and your leftover Grignards are destroyed, well, then you cannot have any more Grignard reactions anymore, right? Because it's impossible, because you just destroyed them. So now, after the lone pair of the oxygen kicks down its electrons and kick out the amide, it used to be an amine now, you will get your ketone. This is the first way. So the first way is to make the intermediate stable. So this is kind of a stable intermediate. And the second, and right here, is the same thing. You can have an dialkyl amide, or you can have instead of the alkyl groups, you can have electron withdrawing groups. Maybe like what, something that can withdraw electrons from the nitrogen. So that will also give you the same product. So we can just copy. So ET, right? Because we have an ethyl Grignard, like so. Same as the logic above. It's just the same thing. Goes through the same chemistry, goes through the same mechanism. So the Grignard attacks stable intermediate, workup destroys the intermediate, gives you the final product. And this is the second method of making your Grignards, well, at only once. So the second method here is you make your starting material more reactive. So in this case, the vinyl Grignard right here, we have a vinyl Grignard. So this is your acid chloride, and you have your vinyl Grignard. So of course it will attack your carbon right there, chlorine. I'm just gonna put the oxygen this way then, so I don't have to move. And your vinyl group. And then what's gonna happen next is it's going to kick out the chloride because it's a good leaving group, and you will get your ketone, which looks this looks horrendous, which looks like this. Well, the reason why it doesn't add twice like esters, it's because, well, when this is done, this product is more stable than this product. Acid chlorides are very reactive. So when this product is formed, your Grignard, it's going to say, nah, we have a better electrophile. And the better electrophile is your acid chloride. So that's why. And you can also add copper 1 ion or some copper 1 compound, copper iodide, copper 1 iodide, copper 1 whatever, to further improve at this efficiency. it's just going to do the same thing. It's more of like a catalyst if you want to have a distinction of it. Well, it's just there to lower the aggressiveness of your Grignard. So it will just only, selectively add once, because, well, you use acid chloride with pure Grignard reagents. Well, sometimes you can have some kind of a mishap, and you might end up with an actual double Grignard addition, but mostly it doesn't. But this is just trying to improve the yield, so that's why they added copper 1 ions, so they could improve the yield, but it's the same thing. And then you have your nitriles. So what's going to happen with the nitrile is that nitrile is just like a carbonyl, but with double bonds. Sorry, triple bonds. So you have so right here I have my phenyl Grignard. It's going to attack the nitrile on the carbon to give me my kind of an imine intermediate. Oh, it also has to be with MgBr. Now I gotta draw it, make it realistic. Normally when I draw mechanisms like these, I only put a lone pair in a negative charge. I am an ionic person. And then, after workup, that's going to protonate your imine, right, to form your normal imine. Then water will come by and attack your imine, forming a tetrahedral intermediate. Well, now since we're doing this in acid, maybe the imine will pick up a proton first, actually. So let's make an imine pick up the proton first, and then let's have water attack later. So that would be more realistic in the acidic medium that we're doing this in. Water will come by, attack this, and then forms a tetrahedral intermediate. Now, after some proton transfer, you will get that your amine will now turn into an NH3, which is a good leaving group. And then your oxygen will just kick it out. And after deprotonation, you will get your final product. There you go. Now for carbon dioxide. Carbon dioxide, you think about it, it's just like a diketone, but on the same carbon. So what's going to happen here is that your isopropyl Grignard will just come here and, attack on the carbon and forms your acid. And this will be after workup, because now the acid is protonated. Good. So those are all of the Grignard additions onto carbonyls. Now the next one is Grignards as an electrophile on SN2 reactions. So you have an alkyl group with a leaving group, maybe bromide, tosylate, whatever, mesylate, whatever. So your ethyl Grignard, right here, that I have, will, do an SN2 reaction. Classic. That's it. I mean, you actually don't have to work up, just copied it, so you don't have to work up this one. And then epoxides. Epoxides are quite a mix. It's quite a mix of a carbonyl and SN2, but it's really simple actually. So your Grignard will attack one of the carbons on the epoxide and kicks up the electron like so, returning the CO electrons to the oxygen, making this product. After workup, like so. But there are some limitations, by the way. Let's say I want to make this diol on the right, starting from this aldehyde from the left. Now you might think, Oh, easy. Just use something like this. Let me just find the colors. You know, just use something like this. What could go wrong? Now, always Grignard in anhydrous conditions. Anhydrous, I mean, you should also say always Grignard with no acidic protons. Always do Grignard reactions with no acidic protons, because when you have an acidic proton, yes, carbon is a good nucleophile in this case, right? As we have established in the structure of the Grignard reagent. But carbon right here is also a good base. So whenever you do a Grignard here, and you have an acidic proton, in this case, it's the proton next to the oxygen. Grignard is a very strong base, and it would immediately react with this acidic proton, and your Grignard reagent will be destroyed into some kind of messy tar. You don't want that. So what you want to do is transform this into something that doesn't have an acidic proton. And one way you can do that is protection. So for alcohols, if you want to protect and use this Grignard reagent, you can use silicon-based protecting groups. For example, trimethylsilyl chloride. Actually, you need to do it before you Grignard it, so there you go. This is before Grignard. So if you want to protect your alcohol, you want to one way you can do that is you can use TMS chloride, which is trimethylsilyl chloride, or you can write it as like this also, Me3SiCl. It's the same as TMS chloride. It's the same thing. And maybe some kind of light base, maybe imidazole, for example. It's imidazole, for example. That's kind of a good weak base to help your protection going. Sounds really weird. So now your alcohol will be protected with TMS, right? With TMS. Now then you can Grignard in ether, and then you can use your starting material, in this case, which is your acetaldehyde, and then you will get, well, not your final product yet, but close. So you will have your hydrogens right here, and then OTMS right here, right? So how do I take the TMS group off? One way to do it is use a reagent called TBAF, which gives off negatively charged fluoride anions. So what's going to happen here is that your TBAF, which contains negative fluoride anion, will attack the silicon, and one thing to note is that the SIF bond is quite strong, so this is very favorable. So the SIF bond is really, really strong, actually. So this is a really good way of the protection. And maybe your your oxygen will grab some kind of acidic proton in the solution, some leftovers in the solution. You have your final product. Same thing right here. So you might say, okay, this is good. You can just have a Grignard, but instead of from the alcohol, you can have it like this, right? Well, same reason you cannot, because you would destroy your Grignard reagents, because, well, Grignard reagents attack on carbonyls, right? So you have carbonyls on your Grignard, it's going to do an intramolecular Grignards, and it's going to destroy your Grignard reagents, and you don't want that. One way to protect ketones is you protect it with acetals. So maybe you can use ethylene glycol or a similar reagent, anything or a similar reagent in acidic conditions. You can protect it into an acetal. You can protect it into an acetal like this. And then you can treat it with Grignard. Then you can treat it with your starting material. And then after workup, oh, I forgot to write workup up there, didn't I? Let me go up there and write it first. Yeah, because it's one bad habit of me. I don't usually write workup after Grignard. It's kind of a bad habit, but you know, it's faster. So then now workup. So to take off your acetal, you can take it off by using acid. You will get back your ketone. And since your acidic workup is, well, acidic, you will get back your ketone. And since your since your acidic workup is acidic, it's just going to give you the ketone back anyway, so you don't have to worry about adding acid later if your workup is strong enough. There you go. And yeah, that's it for Grignard.